Welcome, everybody. This is the first session of Spotlights of our workshop. I'm so excited to share this Q&A. My name is Leonel Rozo. I'm a program chair of the workshop, and I'm also be sharing this Spotlight session. So I would like to encourage, of course, everybody that is watching watch already the talks to post their questions. But I may have some questions, of course, to start with, or maybe to engage the audience to pose their questions. So I think that my first question goes to Matthews regarding the third talk, whose title was anticipating faults by predicting nonlinearity of environment variables with neural networks. So the question refers to the fact that so you were using 60 data points according to the presentation to train the architecture, which was using kind of two LSTMs. And so in my understanding, usually these deep architectures might require more data. And I was just wondering, like, if you thought about using shallower architectures, or maybe kind of a more data efficient or less data hungry, let's say, approaches like non-stationary Gaussian process.
Hello, can you hear me?
Yes, now I can hear you.
Thank you. Sorry about the problems here. I might have gone with
sure, no problem.
Again. But the question was whether I try to use different input data sizes. Is that it?
So what I understood is that you have 60 data points to train the network, right? That corresponds to, I think, like 30 minutes of operation, if I'm not wrong.
Yeah, that's correct.
Yeah, exactly. So I was just wondering, like, I mean, the architecture that you show seems too deep for this kind of data set. I mean, for the size of the data set, of course. And I was wondering if you just try probably shallower architectures or different alternatives like a non-stationary Gaussian process or less data hungry approaches, I would say.
Yeah, we have tried different approaches, different data sizes as well, but we think that this was ended up being the optimal one, especially for the type of data we use. So if we were using perhaps the raw values for the raw estimates for the data, maybe we would have used the shallower architecture or more data points. But I think that by using previous 30 minutes, we ended up getting our result, which was to be predicted at least 30 minutes ahead. So with the 60 data points behind and all the epochs we used, so we were using around a year of data, we managed to get the results that we think it was optimal for this case.
Okay.
So I think that the fact that we use a different metric, we use the nonlinearity offset, it might have been because of that our data is better behaved. I think it would be a better way to speak.
Okay. Okay. Cool. Thank you so much for the answer.
Thank you.
All right. So I will move on to the next question that I have here. This one actually goes to Alex, who presented the work on odds conditional density estimators. I'm not sure, Alex, if you're here. All right. So the question concerns to choosing the artificial probability distribution for a specific problem. So it seems to me that this is a way to introduce inductive bias in, for example, the regression problem that you may have. And I was just wondering, like, for practical applications, how can you choose this artificial probability distribution?
Hello. Hi, Leonel. How are you doing? Could you repeat the question, please?
Sure. To make it short, how do you choose the artificial probability distribution that you have for a specific problem?
Okay. Okay. Actually, we are currently working on this problem, but we are about to prove, like, we just proved a theorem that we're going to put the next version of the paper that says that the instrumental random variable that we use actually is a first guess. And when we run our model, we are likely to improve that first guess. So for example, we have a first model that models the conditional density using another method or a linear regression, traditional linear regression model, for example. And when we apply our method above that first guess, we get a better result. So we have a standard instrumental distribution, which is the uniform one. But when we use a good first guess, we are likely to have a better response in the end. I don't know if it's clear or not, but
No, it was perfectly clear.
okay. Thank
Okay,
you.
thank you, Felipe. It was a great talk. Thank you.
Thanks.
All right, so I think I will proceed to the next question, maybe the last one because we're running out of time. This goes to Ferran Arque, who presented the work on computation of discrete flows over networks via constrained Wasserstein body centers. So, Ferran, are you here? Or Cesar?
Yes, I'm here.
All right. Thank you, Ferran, for the talk. So I was actually wondering, like, what is the motivation of using optimal transport for this problem? So usually the motivation here is to exploit the geometry of probability measures to understand the geometry of the problem. And I was wondering like how this connects actually with your practical problem.
Well, the idea is at least personally, I found out about this optimal transport theory and Wasserstein distances very recently. And we thought, how about we use this distance to solve in a different way this classical problem of transporting mass on a network, and this was like the motivation, find another way with this Wasserstein distance to solve this common problem and exploit these properties that it has to use very powerful computational algorithms to solve it that can be that can perform better or closely to other algorithms that are known.
Oh, okay, I understand. But in that sense, do you compare like against kind of more classical metrics like the Kyle divergence or yeah, other kind of probability measures metrics?
Well, in fact, what we did is write this Wasserstein distance as a KL metric. Well, in fact, we use the regularized version of the Wasserstein distance, which is what allows us to write it as a KL metric. And in turn, we can use these powerful tools to solve the problem. So, yeah,
okay. Okay. Thank you, Ferran. It was pretty clear. Thank you so much. All right, so we are running out of time. I will close the Q&A, but I will definitely encourage all the audience to discuss any further questions or to engage in a discussion for the poster session. And therefore, we're going to go now for the break that is until 6:45 p.m. European summer time. And we'll be here then to watch the next keynote speaker talk. Thank you so much.